All right. Hi, everybody. We have, as you know, been covering some really difficult concepts the past couple of weeks. Sampling distributions, the central limit theorem, uh, null hypothesis testing, p-values and z-values, and I know and t-values and t-tests. And I know that each one of these concepts in its own is difficult to understand. But I think it helps once you're able to sort of start to piece all the pieces together to see, why do we care about the central limit theorem? Why do we need a sampling distribution? So rather than doing review videos on each of those individual concepts, I'm going to try my best to take these really hard concepts and review them and explain them in a way that I hope makes some sense while I tie them all together. Right, so this is going to be it's going to be a challenge. Stay with me as much as you can, and again, this is recorded. Great, so you can always go back and watch parts again that are confusing. But I know that at least some of you are like right there on the verge of getting it, and I really hope that by like I said, tying all the pieces together, uh, I'm hoping that kind of gets you over that hump to where you start to go, oh, I think I get it, or it starts to make a little more sense. So that's my attempt with this video. I I hand doodled all of it on my sketch pad. So, and I am not an artist in any way, as you can see from this screen. But this is my attempt to try to boil these really hard concepts down into something a little more digestible. So I hope this helps. So here we go. So starting back at the very basics, we have some population that we're interested in, right? And with research, we start with a question. We have a question about something. And in order to answer that question, we have to know some measurement from a population, from that population that we're interested in. So this might be the mean of some variable of interest, like we might be interested in anxiety levels among this population, or well-being, or IQ, or GPA, right? Whatever that dependent variable, that variable that we're interested in, that we want to know more about, you know, is it, are there differences here, or is there something interesting going on with this variable that we're interested in? We need to find a way to sort of measure it first, right? In order to answer some questions, we have to have measurements. So we have a population, that's the whole big group of people we're interested in, and we want to measure something in that population. Now, since we can't really measure everyone in the whole population, as we talked about before, it's just about usually impossible. What we do instead is we gather a measurement from a sample of people. So we select different people from that population to be in our sample. It's like when you go to Costco and you get a little sample of something, you're not getting the whole thing, but you're getting something that hopefully represents the whole thing, right? You're getting that little piece to represent the whole thing, so you have an idea of what's going on in the whole pie or in the whole whatever, right? So since we can't measure the thing in the whole population, we take this sample and we measure all of the individual people in that sample, right? We can't measure everyone in the population, so let's just take a group of people and measure it among them. Now, of course, I have my little asterisk here. We want to keep in mind that how we select that sample, whether we're randomly picking people out or we're just walking around saying, hey, you want to be in my sample? That matters for trying to ensure how representative our sample is of the whole population. So for example, let me think, I'm so bad at coming up with examples on the fly. I should have thought of this beforehand. But let's say you're at Costco and you're walking around getting samples, and they are like, let's say it's a pie, right? They have this beautiful full pie that they want to encourage you to buy, and to encourage you to buy it, they want to say like, here, taste how good it is. But instead of slicing you a slice of the pie that contains all the different pieces of the pie, they just scoop off a little whipped cream from the top and give that to you. Is that taste that you're getting, that sample, is that representative of the whole thing that you're trying to taste? No, it's just one little piece. You're missing a bunch of other components. So that's what I mean, is when you take that sample, how you take it matters, because you want to make sure that you're getting all the different components of that thing that you want to taste, right? So this is just a caveat to say how we select that sample matters for how representative, like that conclusion that we get from our sample, whether it's tasty or not, if we want to buy the pie or not, that depends on that kind of sliver or cross section that you're getting from the whole thing. So this is really more of an advanced or more of a research methods topic. So if you go on to a research methods class like Psych 201 at Valley College, then you're going to learn all about different sampling techniques in that research process and how they kind of affect those conclusions you can draw from your sample about the whole big population. So just a little caveat, but as a reminder, we can't take the whole population, so instead we select our sample and measure among the sample. Now, once we have that sample gathered and we have the measurements for all those people, since we're talking behavioral sciences, we're usually talking people. Once we have all those measurements, then we can look at those measurements that we got in our sample, and then, like I said, try to draw some conclusions about our population. So we look at that sample, and we can take each of those measurements and plot them out on our number line, as we've been talking about doing, create our histogram where, we have, maybe this is person with that 58, and we got a 61 over here, and there's a 43, and there's a 70, and 85, right? We plot out those scores and see how they stack up in our histogram. We look at that shape, and we try to, understand what's going on in our sample. Now, kind of the problem is that's just one sample. So how can we draw conclusions from just one sample? Because again, like, it depends on who ended up in our sample in the first place. How do we know we didn't just get a really weird sample? And it's not very representative of what's going on if we were to look at the whole population. So it would be nice if we had something to compare it to. Okay, now bear with me here. So I want you to imagine that we could take hundreds of thousands of different random samples from that population that we're interested in, instead of just one. Wouldn't it be cool if we could do like samples and samples and samples, samples? Of course, in the real world, that's not really possible because each of these samples takes effort and time and money and all this stuff, right? So, but it would be really nice if we could do that and then look at all those many possible outcomes that we get, right? We get this outcome with some certain mean for sample A. This is what it looks like for sample B, and that's the mean we get. Here's what sample C looks like with the mean, and so on. We take just a bunch of samples, different random samples. Now, once we have all those samples and the sample means for all of those different samples, what we could do is then take all of those sample means that we see and plot them out on a number line, just like we did to get our sample distribution, where we took a sample and then we plot out all the scores. Here, we could plot out all of those means on a number line to see how those pile up. So keep in mind that now this distribution that we see here, this is no longer a distribution made up of individual people. Okay, I cannot draw very well on this using that. So this is not individual people like we had in our sample. This is now a bunch of sample means. So what we're doing is we're saying, okay, here's this sample, here's what it looks like, here's the mean, whatever that works out to be. That's what the middle is for this group. Now I'm going to plot that mean down here on my number line, wherever it falls. Now for this sample, we see the middle is here on my distribution, and here's my mean. So I'll go ahead and plot that wherever it falls on my number line. And then same thing here. Let's plot this middle. And then we plot the middle for, the next one, and so on. So imagine that we just take each of these centers, each of these means, and we just drop that value, whatever that mean value happens to be, we find it on our number line, and we add it to our distribution. So each of the little points of data that make up this distribution, these are all sample means. Okay, so no longer individual people. Now they represent the mean of a whole sample. So once we plot out all those means, like I said, we can see how do they pile up? Where are the means that happen a lot? Where are the means that almost never show up? We can see who are the popular means, the ones that kind of stick out in the middle, and who are those weirdo means that maybe we get a mean way out here. And it's like, whoa, that's weird. That's not like most of the other means. It's possible, right? Because we can always just get a super weird sample. But a lot of the times, those weird scores that we see in a sample are getting canceled out by the fact that we're taking the mean. We're balancing them out, so we get lots and lots and lots of middles all stacking up. So this distribution is made up of sample means, and so this is what we call, it's got that special name, the sampling distribution of means. The sampling just means take lots of samples. So if we were to take all the different samples, plot them out, then we could see, okay, so what do the means look like? Where do they pile up? Which ones are the ones that we see a lot? Which ones sort of stick out? Okay, so, and we're going to call this the sampling distribution of means, or the SDoM for short. So once we have this situation, right, this hypothetical situation, and we've got our SDoM, our sampling distribution of those means, kind of assembled, then we know some cool things about that SDoM. There are some things that are always going to be true thanks to the central limit theorem that somebody super smart at some point, went about and proved, so we don't have to do that proof again. But we did see it in action, right, in one of those classworks where we were using the simulator. So that illustrates, what's happening in the central limit theorem. So thanks to the central limit theorem, we don't need to know what the shape of this population distribution is. Doesn't matter if it's normal, if it's really skewed, if it's bimodal, if it's doing something real weird, right? it kind of doesn't matter what the population distribution looks like, because when we take all these means and all these centers and we plot them out, then this shape of the SDoM, as long as our sample sizes are like a minimum of maybe about 30, right? As long as they're big enough, then this shape is always going to come out this nice, pretty bell normal shape. So again, doesn't really matter to us how the population is shaped, because we know when we take that sampling distribution, as long as our samples are big enough, we're going to get this nice, pretty normal shape. Okay. So some more things about the SDoM that help us. We also saw in that simulation that the mean of that population is also going to be the mean of our SDoM. So if we knew what this mean was, we could assign that mean there, right? If I know that the mean IQ in my population is 100, then the mean value for my SDoM is also going to be 100. So that's pretty handy. And we also know that this SDoM that we see, when we're piling up all those middles, what's happening is it's getting tighter and tighter around the true population middle, right? That true population mean. So when we pile up all those values, then our SDoM shape is going to be like taller and skinnier than whatever that shape of that population is. We're basically, we're drawing in, getting closer and closer to that mean. If we have a low sample size, if we don't have very many people in our sample, then it's going to be a fatter curve. Whereas if we do have a high sample size, it's going to be a taller, skinnier curve. So the shape of like how tall and skinny it looks, that's going to depend on how many people are in our sample. Now the standard deviation, that average spread around our mean that we're now using like a tape measure, right? So the standard deviation of our SDoM is called the standard error of the mean, and I abbreviate that as SE, but sometimes in other stats books and stuff you'll see it abbreviated as SEM. So this is the standard error of the mean, which is the standard deviation of the SDoM. I know all these S's and D's and things get confusing, but if we're trying to say, okay, how wide is this SDoM that I get that's made up of all these different sample means that have been plotted, that's called the standard error. Okay. Now, the standard error has a specific formula that goes with it that helps us figure out, how skinny is this curve? In other words, right? If we have a really high standard error, that means it's a fat curve. If you have a small standard error, then that would imply that it's a really skinny curve. Now, this formula that we have to find out how wide that standard error is here, right? So these look very similar, except for one key difference, which is the symbol that is on the top. So those symbols correspond to whether we know the true population standard deviation or whether we're having to estimate for it based on the standard deviation that we get from a sample. Okay. But in either case, these formulas both work the exact same way. We plug in the standard deviation for the population that we have. It could be, we know for sure it's sigma. We know what it is. We plug that in and then divide that by the square root of our sample size. Or if we don't know what sigma is, but we took a sample and we're using that to estimate for what we think sigma might be, then that's what we use that S statistic. But again, we take that population standard deviation, in this case an estimate, and divide by the square root of the size of our sample. Now, this is, whether we know that sigma or we're estimating it, this is what determines the resulting shape of our SDoM distribution. If we know that standard deviation from the population, that sigma value, then we plug that in. Then we know that the shape of our SDoM will be the Z distribution, that standard normal distribution where the mean is always 0. One standard deviation up has certain qualities, one standard deviation down has certain qualities. The standard deviation we can set to equal 1. If we don't know the standard deviation of our population and we're estimating for it by adjusting our sample standard deviation a little, so going way back to that early sampling or standard distribution assignment when we talked about dividing by n-1 to kind of fudge our estimate a little bit to make it a little bit bigger to accommodate for the fact that we know that the sample is not going to be quite right. That's what we're referring back to here. If we don't know that true population standard deviation, but we're able to estimate for it using S, then we go ahead and we use that S in our formula, and we know that our resulting SDoM shape, the curve we're going to get, is going to be T-shaped rather than Z-shaped. Now, you may wonder why does it matter? Because they both look pretty normal, right? Well, we'll get to that in a second. I forgot I have this part first. So we've got our sampling distribution of means. We can sort of figure out this mean of it based on the mean of the population. We can figure out how wide it is, right? If we're building a model, since we can't really take tens of thousands of samples, we don't really need to, because again, number one, we know it's going to be normal, right? So we know the shape without having to actually take all those samples. That shape, then the center, we know the mean is equal to the population mean. Okay, so we're good there. And then for that spread, well, we know the formula for figuring it out, which is that standard error, which is that standard deviation divided by the square root of our sample size. And whichever version of that standard deviation that we have, we'll use. And that tells us, is it going to be a Z shape or a T shape? Once we have this SDoM modeled, because we can put this model together, like I said, without actually taking all these different samples. So once we build this SDoM model that we want to compare to, then we can use it to find probabilities associated with certain things happening, with certain results occurring. So I like to think of it, I've been watching a lot of baking shows recently, so that's probably coming through in my examples. But you can think of it like slicing up a cake and figuring out how much of that cake, what proportion of that cake is in a particular slice, right? You can imagine we could slice it up into different slices and say, how much cake is in this slice? Or if I take this slice over here, how much cake is in this slice? If I sliced it right here and I wanted to see how much cake is in this slice, well, since we're cutting it in the middle, we'll know that this is 50% of our cake, right? So you can imagine it as we want to know how much of the cake is in a given slice that we're taking. And the slice that we take depends on the question that we're asking. So some examples of slices we might want to know: what's the probability, what's the proportion associated with this slice down here? Versus I might want to know, what's the probability associated with being between this value and this value? So we're looking at a middle slice. Or maybe we're looking at, okay, how much of this cake is above a certain value? So how much is in this slice here? Now this is where it matters whether we're using a Z curve or a T curve, because these probabilities associated with our slices are going to be a little bit different if we're using a Z than if we're using a T. So this is where it starts to matter if we're using sigma for our population standard deviation, or if you're using S, our estimate for the population standard deviation. If we know which one of these, then we know which one of these to use the probabilities for. Because again, those probabilities are going to be a little bit different for these ones than they are for these ones. That's why we have different tables for Z's and T's. So let's say that we do know that population standard deviation. Usually this is not the case. I will let you know. Sometimes it is. Like if we design a test, if we come up with some sort of measurement and we design it in a way that we know that the overall population is going to be spread out a certain amount, then we can use it. But most of the time we're going to be doing T's. So we'll kind of come back to that, but it helps to understand this Z first because it's kind of like a good basis. Right? So if the SDoM is Z-shaped, because we know what sigma, our population standard deviation, is, then the shape that we get, that curve, is always exactly the same. And so if that curve never changes, it's always exactly the same, then this means that we can figure out these different probabilities for all these different slices, and those probabilities are always going to be exactly the same. They're not going to change at all, because this Z, there's only one Z curve, and it always looks the same. It's that standard normal curve. So, for example, we often want to know where to slice, right? Where do we want to cut our cake in order to cut off that outer 5% of scores? So 2.5% of our scores down here, 2.5% of our cake, and 2.5% up here, because when we add those 2.5% plus 2.5% together, what does that give us? 5%. Right? So we often want to know, where would I slice if I want basically to get the middle 95% and separate it from those outside chunks? Right? What value, where do I need to slice here in order to capture that top 2.5% and bottom 2.5% and cut them off from our middle 95%? And this 5%, of course, is coming from that alpha that we use, right? That's what determines how much we're chopping off at the ends. So with a z distribution, since that z-curve is always the exact same shape, it doesn't change at all, doesn't matter how many people are in your sample, it's always going to be the same size because we know exactly how wide this is. There's no question about how wide it is because we know what that sigma is. All right, so we can be real, we know we're being exact here. There's no wiggle room. We're not estimating anything. We know how wide that is. So that means that we can set this curve and we know where we want to slice off those bottom and top 2.5% is always going to be at negative 1.96, right? So these are the z's. Once we convert whatever measurement we're using into these z's, we know, okay, where z is negative 1.96, slice. Where z is positive 1.96, slice. And that's going to give us our outer 5% versus our inner 95%. Those numbers, 1.96, always the same because that curve is always the same. Now that's not true for our T-shaped curves. Now, because we're estimating using S, this means that we're not necessarily exactly sure how wide that standard error is because we don't know for sure what the true population standard deviation is. So we're kind of fudging a little bit, right? So we're estimating, and how many people we're using to estimate is going to affect how good our estimate is. If we're using only like 3 people for a whole population, then it's maybe not going to be the best estimate, right? So in that case, we're going to need to make our curve a lot fatter just to be sure that we're really capturing or estimating well for that population standard deviation. If we have like 10,000 people in our sample, if we have a huge sample, then we can be pretty confident that our estimate based on that sample is probably going to be pretty dang close to the true population standard deviation. So in that case, we know more clearly how wide that SE really is going to be. So if the SDoM is T-shaped, then because we have estimated for that population standard deviation using S, then those cutoff points that we use on and the associated probabilities and stuff, they change depending on our sample size. If we have a small sample size, that means we're estimating more, right? We're less sure that we're getting the true thing, so we have to estimate more. We're kind of fudging it a little bit more. So in that case, our T-curve is fatter and flatter because with a small sample size, we're having to fudge more on that population standard deviation estimate. So we might get a T. So when N is low, we might have a T-curve that looks a lot fatter and flatter. If we have, right, so in this case, that means that in order to cut off that outer 2.5%, we might have to cut a little further out to really get 2.5% and 2.5% and 95% in the middle. So instead of cutting at 1.96 like we do with Z, maybe if we have a low sample size, we're actually going to cut further out at negative 2.12 and positive 2.12. Because it's squished and it's flattened out, we got to go further out to get that ultimate 5%. Now, if we have a bigger sample size, then we're not fudging that estimate as much. So the curve that we get for our T is going to look a lot closer to, for example, like the true normal Z population. It'll be a lot closer. And so those probabilities are going to be closer to the Z. And again, this is when we have a higher sample size. So in this case, when we're estimating, we have a better estimate, in other words. So we're able to be a little bit more precise. And so we don't have to go quite so far out. It looks more like a Z-curve. So maybe those cutoff points are not so far out because it's not so squished and flat. We have more of that 95%, concentrated higher here. Then these numbers will get closer and closer to what we would use if it was a Z. So they'll get closer and closer to that 1.96 that we would be using if we knew for sure what that population standard deviation is. So maybe at some point, it's maybe for this one, we're pretty close, and it's actually, we're cutting at 1.98 instead of 1.96. Right? So the sample size changes the shape of our T. It depends. So we might have a fat one or a little bit skinnier, Like at some point, it's going to approach looking like a Z. Once we get, so if we had a really big sample size, at some point, the Z and the T are going to be essentially the same thing. But which curve we're looking at, which T curve specifically, how fat it is, depends on how big our sample size is. If our sample size is small, it's going to be short and fat, and we got to go further out to get 5%. If our sample size is big, it's more like a Z, and we don't have to go so far out. We get closer to that 1.96 cutoff. Hopefully that's making a little sense there. And I'll get to this again later, but you may be wondering, why do we care about this 95% versus the outer 5%? Again, that's based on our alpha value that we're using, that 0.05. That's what's telling me I want to chop off the outer 5% from the inner 95%. All right. So hopefully you're still vaguely with me. So we've got our population, right? And we can model a standard, the standard deviation and the sampling distribution. I know those SD and SD, even I get tongue-tied over it. So we have our population of interest, and from that we can create a model of our sampling distribution of means, our SDoM. We can figure out whether that SDoM has a Z shape or a T shape based on whether we are estimating for the standard deviation of the population or if we really know what it is. All right, so that tells us the exact shape of our curve. If it's a T, the exact shape depends on how big our sample size is. If it's low, it'll be shorter and fatter. If it's high, it'll look more like Z. We know that the mean of our SDoM is going to be the same as the mean of our population. So we can just put that baby into our model. We can figure out how wide our SDoM is by plugging in the population standard deviation divided by the square root of the sample size. So, and again, the bigger that sample size, the tighter in, the closer in, the smaller that SE is going to get. Let's think back to that central limit theorem simulation. And remember, we had that like n equals 2, n equals 10, n equals 25. And as that n goes up, that curve gets tighter and tighter and tighter around that middle. Now, it would be super cool, this would be really nice, if we could figure out how likely it is that our true population mean, right, that's the thing we're really trying to figure out, is some value. Like, I think that, IQ among this group is 110. It would be really cool if we could figure out what's the likelihood or what's the probability of that being true. The problem is we don't know what that population mean is to start with. That's really what we're trying to figure out. Right? So we have to do this kind of backwards. We can't start by assuming our mean is a certain value because we don't know what that value is. Right? Just like when we were talking about who is Tim? Is it the guy on the left or the guy on the right? Well, we don't know if everybody ever answered that question. We don't know what that true population proportion would be. So we have to work backwards. And this is why this way of thinking is so hard, because again, we're going backwards here. So instead of saying, what's the likelihood that it is this particular value that we don't know, we have to say, okay, well, how likely is it to be something that we don't think it is? This is the very backwards part. So we sort of figure out how likely is it that our mean is something that we don't actually think it is. And that thing that we don't actually think it is, that's the basis of our null hypothesis. As a reminder, we use this little abbreviation H0 or H sub 0. That's just shorthand for null hypothesis. So first we think about, well, what do we think is not true? What do we think is not happening here? And then we try to show that that's unlikely, right? So we basically want to show it's very unlikely that the population mean is equal to our null hypothesis mean. Because if it's really unlikely that it's this thing we don't think it is, then that must mean it's something else, which is what we really think it is. Again, this is very confusing, right? So we don't start by assuming it's what we hope, what's interesting. We start by assuming that it's boring and that it's this thing that we don't want it to be. So we start out assuming the opposite of what we think is true. We start by assuming that the null hypothesis is true. Right? So when we build our SDoM model, we're going to start by assuming the null hypothesis is true. And the null hypothesis is always that boring hypothesis, is the hypothesis that nothing's happening, that there's no difference, that there's no relationship, right? It's the this is not very interesting hypothesis. It's not the one that we're really suspect is happening, okay, which is why we're doing this research in the first place. So in other words, if we think the mean of a population is different from 100, right, that would be our alternative hypothesis. That's the one we really are interested in. We have to start by assuming the opposite. We start by assuming the mean is 100. The mean is equal to 100. If we think that two populations have different means, we start by assuming the opposite. We start by assuming that, no, those means are equal. They're not different. So we always start by assuming the opposite of what we think is true. We start by assuming that the null hypothesis is true. So when we build this SDoM model, because again, we don't have to really make an SDoM by taking all these samples. We know enough about how they work to be able to put the model together. When we build this model, we're building it to compare to, right? We want to eventually, we'll get a sample that we can compare to this. We want to compare to the SDoM assuming the null hypothesis is true. And the reason why we do that is because that null hypothesis, that boring hypothesis, we know what it looks like. We know what mean equals to 100 looks like. It means the mean is equal to 100. If we say the mean is not equal to 100, well, where do you start? Do we start with assuming it's 101, 108, 96, 99? Right? There's so many possibilities. We would have to build a model for all the different possibilities, and that's just not really possible. So we start with a thing that we think is not true. Assume the opposite. Okay, assume the boring thing is going on. Assume the things are equal. Assume that it's equal to this value. Oh no! Spoiler alert. You're not supposed to see Snoop Dogg yet. So we've got our population. Since we don't know what the mean is, we start by assuming what the mean would be based on the null hypothesis. Okay, so when we're building our SDoM, this mean that gets put in is based on the null hypothesis. So if we think for reals that this population has a mean that's not equal to 100, if that's our alternative hypothesis, our research hypothesis, we start by assuming the opposite, that it is equal to 100. So then it would be that value that gets put into our model. So we assume the null hypothesis is true, and we use that to model our SDoM. Now, once we have built this model, right, if we can figure out what this model would look like, what we're actually going to want to do then, right, it sort of gives us something to compare to. That's what this SDoM ultimately is for, right? We want to know, well, if the null hypothesis was true, what kind of results, what kind of means would I expect to see? If it's true, I could see, this mean here is pretty common. If it falls over here, that's pretty common. But if I end up getting a mean that's way out here, that's going to tell me that's weird. It's in my weird region where I'm going to reject that null hypothesis. Right? So this gives us something to compare to. We're comparing to the thing that we think is not true. And then we want to show, oh, it's really unlikely that this null is really true because we got such a weird result. The chances of that are really small, so we can reject the null. So we take a sample from our population, a real empirical sample where we really get people and we measure something in those people. We figure out, okay, in this sample, what does the sample mean that I got? I got this sample mean X bar. Okay. So we take a sample from the population of interest, calculate the sample mean, and then we need to compare the sample mean that I got. Where does this fit in to my SDoM that's based on the boring hypothesis. Okay? Compare our real sample mean with all of these hypothetical or simulated or modeled possibilities for the sample means that we might get if the null hypothesis is true, if this is 100 or whatever it is that we're testing against. So we build this model based on the assumption the null is true. We take a sample, calculate that sample mean, and then say, okay, well, where does this sample mean figure out in this, where does it fit in this model? Does it fit somewhere in the middle? In which case, yeah, that's pretty reasonable that we could get this mean if this is true. In which case that's not weird. So yeah, this could be true. Maybe that mean lands over here. Again, if it's in that inner 95%, then that's not very weird. Then maybe that's true. We totally could get a result like that. If we get it over here, again, we could get that result. It's not that unlikely if the null is true, so we can't reject the null. It's only when we find that it's in our cutoff points, in our cutoff regions out here at the ends, slices of cake that we chop off. Those are the weirdo slices of cake. So if our mean ends up out here, then we can say, well, the chances of that mean being way out here, if this is true, those chances are really low. And since those chances are really low, I don't think this is true. I'm going to reject it. I'm going to say it's not equal to 100. Right? Just like if this mean, if it came up over here in this weird slice of cake, if it's outside that middle 95 region, then we're saying this is too weird, like to have happened by chance, to get a mean way down there if this is true. It's so weird, I no longer think this is true. I think it's the opposite. Okay? So very, very backwards kind of way of thinking. But we want to see, okay, we have some population that we really don't know something about. We think something about it, but we're going to assume the opposite. We build a model that we can compare to based on this opposite thing, this null hypothesis. Then we gather a real sample and we see how did that sample turn out. And then depending on where it fits in here is going to tell us whether we think it's likely to have happened based on the null hypothesis. So this is it's fairly likely. And then outside those cutoff points is where it's unlikely, where we have a really small probability that it would happen. And so we end up rejecting the null hypothesis. So if it's in that inner 95%, and this corresponds to if our P is above 0.05, that means it's somewhere in this middle area, then we can't reject the null hypothesis because it could happen. It's not super unlikely. If it's in one of these outside slices where there's only 2.5% here and only 2.5% here, there's not very much. If it's in this outer 5%, then we say, nope, that's really weird to have happened. I'm going to reject the null hypothesis. I think something really is going on that's other than this. I think it's not this. And when we reject that null hypothesis and say, no, I think it's not the boring thing. I think it's it's the other thing, the thing that we're really interested in, that's when we call it significant, right? It's significantly weird enough, it sticks out enough that we say, no, I don't believe this anymore. I don't think this null hypothesis is true at all. I think it's the opposite. Now, sometimes we just want to know whether a population mean is equal or not equal to some value. And that value is based on our null hypothesis, right? It's equal to 100 or it's not equal to 100. Or it's equal to 0 or it's not equal to 0. We figure out what that value is according to the null hypothesis, and we use that to build our SDoM and then to test. So in a case like this where we just want to know, is this population mean equal to this value or not? In that case, we do what we've been describing. We take one sample, we calculate that sample mean, and we see where does it fit in. Is it weird or not weird? This that we've been describing, this scenario is called a one sample test because we only have one sample. We take one sample, we compare it to our null hypothesis SDoM, and we draw a conclusion about our population mean based on this result. Now, more often, we're not actually interested in, is the population mean this value or not? What we're often more interested in research is whether different groups are the same or different in terms of their values, their measurements, and their means. So more often, we want to know whether two populations, men and women, parents and children, people who took a review statistics course versus people who didn't take a review statistics course, two different groups, right? We often want to know whether two different potential populations or groups, do they have the same mean or different means? Are they the same as each other or different from each other? That's often what we want to know, right? Maybe there's this, maybe for struggling, readers in elementary school, they come up with this program that's supposed to help them learn how to read better. So we give one group this program and we don't give another group the program, and then we compare them and see, well, is there a difference between these two without the program versus the program? That's a way of seeing, like, did the program really work? If it worked, you expect the ones who got the program to do better, to have a higher mean in however you're measuring their reading. Right? So that's more typically the kind of question that we ask in research. Are these groups the same or are they different? Now, in this case, to test this kind of hypothesis, the hypothesis is no longer that the population mean is equal to some number. Instead, what we're saying is we think the population mean for one group is that the same or not the same as the population mean for another group, right? It's a different kind of question that we're asking, so we set things up a little differently, but it's the same basic underlying concept. So if we have population A and population B, and we want to know these two populations, are they equal on this thing or not equal? We don't know. Usually when we're asking this question, it's because we think they're not equal. We think there's a difference. Women score higher in depression than men do. They're not equal. Or if you take this program, then the people who took the program are going to be different from the people who didn't take the program. Right? So usually we want to test, are they different? But since we can't sort of qualify, well, how different? Are they a little different? Are they a lot different? We start with what we think is not true. We start with assume they are not different. Assume they are equal to each other. So to test this, we have to take two samples. We need to take a sample from our population A. And then for this sample A, we can figure out, well, what's the mean for this sample? And we take a sample from population B and say, okay, for this sample, sample B, what is their mean? And really what we're going to end up doing is sort of comparing these two means and trying to determine how likely is it that they really come from different valued populations, or could they just as easily, any differences we see, could be explained if they were equal. So our sampling distribution that we want to make, that we want to model to compare to, is now not made up of, it's no longer sample means. It's no longer sample means. What it is it's the difference between sample means. So if we had one sample mean minus another sample mean, the difference between them. So all these little dots in here are now mean differences between two means. Our sampling distribution, in this case where we take two samples, is made up of those hypothetical differences we might see between two sample means. We model this distribution based on the null hypothesis that really these two groups are equal. They're not different. The mean for population A is going to be the same as the mean for population B. Nothing interesting is going on. Or in other words, there is zero mean difference. There's zero difference between the mean of population A and the mean of population B. This is our null hypothesis in this case. And again, this is because we know what no difference looks like. If there's no difference, then there's zero difference. We put that 0 as our center. So the null hypothesis, again, we're doing the sampling distribution of mean differences, because this distribution is made up of the differences, hypothetical differences between two means. And we start out by assuming there's zero difference between the means of these two populations. There's no difference. In other words, they are the same or equal. So our null hypothesis in this case is that the mean for population A is equal to the mean of population B. And so in other words, if we were to subtract one of these from the other, it's just going to be 0. There's zero difference between them. So then once we've modeled this sampling distribution, and most of the time we're going to be doing t, because like I said, most of the time we don't know for sure that population standard deviation and we're estimating. So most of the time we're going to be using t here. So you'll see we're going to kind of move away from the z's and focus on those t's now. So we've got our two hypothetical populations. We want to know, are they the same or different? Assume they're the same. Create a model based on the assumption that they're the same. Take a sample from one, calculate the mean. Take a sample from the other, calculate the mean. Then compare these two means to find the difference between them. So how different are these two means? Maybe we get that they actually come out exactly the same, in which case our mean difference is going to fall right here at the 0 mark. There's 0 difference. Or we may find that the sample mean for A is way higher than the sample mean for B. So when we take the difference, that mean difference ends up over here somewhere. Or maybe we find the sample mean for B is bigger than the sample mean for A, in which case, when we subtract, we get a negative difference, and so it's down over here. All right, so what we want to do is we find that difference and say, okay, where's the difference? This way would be like if B is bigger than A. This way would be if A is bigger than B. And we want to find where does the difference that we really see, where does that land? Is it in our middle 95 not weird area? Or is the difference that we see between these two so big and so extreme that it lands in one of our rejection regions? Like A is so much bigger than B that when we find the difference, that mean difference is way out here. And we go, that's really weird. It would be super, super, super weird to see a mean difference this big if those populations really were not different. Then that would be weird. Like really weird. Weird enough that we're going to say, I think there is a difference between these groups. If B is so much bigger than A that it lands out here in this rejection region, again, it would be so weird to see that big of a difference if this is true that I don't think this is true. I think it's not the null. I'm going to reject the null and go with the opposite. So I would reject the null that they are equal, those population means. I would reject that and say, I conclude they're not equal. They are different. It all depends on that p-value we get. So if it lands in this middle 95%, that corresponds to when p is bigger than 0.05. The probability, the proportion in here, is higher than 0.05. If it lands out here, this represents when that probability of happening is lower than 0.05, and that's when we reject. So I know with this visual stuff, like for me, it really helps to draw things out, to visualize, to label things, to figure out, what's in the middle and then where does my thing fall. Most of the time, we're going to be using computers, right? We're going to be using JASP or some other statistical software that does all this work behind the scenes. We don't really need to do all of this stuff by hand because we got computers. So what the computer does is, okay, it does this process. It says, okay, assuming they're equal, now let's look at the mean for this group and the mean for this group. If we assume they're equal based on this sample size, this is the sampling distribution. What's the difference between these? And then it figures all this out. It figures out whether it lands in the middle or whether it lands in the rejection regions. So once it figures that out, the computer then spits out the p-value for us in our output. And that p-value is what we use to tell us, well, is it in that middle or is it in one of the rejection regions? So the p-value is what we use to guide our decision on whether we reject the null hypothesis or not. So if we've got our sampling distribution based on our null hypothesis, if the p-value we get is higher than 0.05, that means that we're landing in the middle and we do not reject. If the p-value that we get from the computer is smaller than 0.05, that means it's either in this slice or it's in this slice. And those are the cases where we're going to reject the null. So we won't necessarily see the picture, but when we get that p-value, that's telling us, is it in the middle or is it in the rejection regions? So if that p is lower than 0.05, that means it's in the rejection region. So all we really need to know ultimately is, what is that p-value? If it's above 0.05, we can't reject the null. If it's below 0.05, we do reject the null. So we use the p-value to guide our decision on whether to reject the null hypothesis, H0, or not. And you're going to hear, I'm going to start referring to this guy as Ho, because it looks like Ho, right? So as a reminder, the p-value is the probability of getting a result like the one that we really get in our real samples. Oh, we get a certain result and we can calculate what's the difference between those means. That's our real result. The p-value is what's the probability of getting that result that we see, or even more extreme than that, assuming that the null hypothesis is true. If that probability is low, then we no longer assume the null, low enough, we no longer assume that null hypothesis is true. If that probability is above 0.05, well, then we can't reject the null because it's reasonable enough that it could happen. And again, I like to use this little acronym of PRINT because this P, if you could ask so many people who have had stats classes what P is, and even people who teach it sometimes tell it to you wrong, right? It's very easy to misinterpret what this p-value is. Super hard concept. It's the probability of the result that we see, or something more extreme, if the null hypothesis is true. It's the probability of our result if the null is true. And so I use this little acronym to make sure I'm getting it the right way around. It's not the probability of our result if it's not true, if the alternative is true. It's always if the null is true, because we start by assuming the null is true. And then if it's super, super weird, then we can stop assuming it. We can reject that assumption. Very, very backwards way of thinking. So to help us remember, because I know this decision is really hard for a lot of people, wait, if it's bigger than or less than, do I reject, do I not reject? So this is where Snoop Dogg comes in to help us out. If you're trying to remember, do I reject or not? Do I reject the null hypothesis or not? Let Snoop Dogg be our guide. So if the P is low, the Ho must go. So let's see, here we go. Oh, yep, that is where I wanted to be. So, as Snoop says, if the P is low, then the Ho must go. We don't got a home no mo. you know? So if P is low, if it's below 0.05, then we are going to reject the hoe. We're going to reject that null hypothesis. That hoe gotta go. And if we reject the null hypothesis because it's pretty unlikely given our result, then that's when we say this is statistically significant. Okay. So use this little mnemonic to help you. Once you get that p-value, p equals something when it's spit out by the computer in your output. We want to know, okay, well, is it above 0.05? In which case, can't get rid of the hoe. If p is below, if it's lower than 0.05, if the p is low, then that hoe must go. We reject the hoe. Okay, so hopefully that helps you to remember that a little better. And I really hope that you at least picked up something from this video that makes a little more sense now. And like I said, this is the real tough stuff. So if you're still not there, that's okay. Each time we go through it, I just want it to get a little more clear and a little more clear. So I'm hoping that this long explanation, you can sort of see, okay, an SDoM, the sampling distribution, that's a distribution made up of a bunch of sample means. And we start by assuming that the null hypothesis is true, and that's how we build that SDoM model. And we can build it without actually doing it thanks to the central limit theorem, right? That's basically, thanks central limit theorem, now we can just build this model without actually having to do all the hard work behind it. Once we've got that model representing the null hypothesis, if the null hypothesis is true, these are some results that we might see. Some results happen very often and are therefore, pretty likely to happen. And some results only happen every once in a while. They're really rare and they're really weird. So when we take a real sample, we can figure out, does this look like one of those samples that happen often? In which case, we got to stick with the null hypothesis. Or does this look like one of those really weird samples that almost never happens? In which case, the likelihood's so low, we don't think the null hypothesis is true anymore, and we reject it. We go with what we actually think, the interesting thing that is happening. So I'm hoping this starts to tie those concepts together in a way that we can see, like, why do we need all these things? How does it all fit together so that we can ask a question, get some data, and then draw a conclusion to try to answer our question. So let me know any questions you have. I'm sure there are probably many. And keep in mind, Snoop Dogg, if the P is low, the hoe must go. And I hope that this helps. I'll talk to y'all soon.